Awesome. Thanks everybody for joining us today for this webinar on design guidelines for microfluidic device manufacturing. Excited to introduce Josh, CEO over at Parallel Fluidics, to talk through some of these design guidelines and a little bit about what Parallel has to offer. A couple of sort of housekeeping items before we get started. If you do have any questions, there is a Q&A button at the bottom of your screen. You should be able to click that and type in your question there. We'll have a dedicated question and answer session at the very end of the presentation. So feel free to drop questions in there throughout the presentation, and we'll get back to you at the end of the presentation there. Additionally, the webinar is being recorded, so we will have a recording available and sent out to all attendees so you can review it later as well. With that, excited to turn it over to Josh and have him kick off the webinar.
All right, awesome. Well, thanks a lot, Nick, and thank you everyone for joining us here today. So just to get started here, the goal of this webinar is to share some best practices that will help make all of your development processes easier as you are developing microfluidic products. So the quick agenda for today is I'll talk quickly about my background. I won't bore you with that for too long. We'll talk a bit about manufacturing processes at a high level for microfluidic devices, and then jump into some real kind of nitty-gritty design guidelines and best practices to really improve your chances for success. And then we'll wrap up with just a quick bit about our work here at Parallel, and then the question and answers session. So my background is I'm the CEO of Parallel Fluidics. I'm a mechanical engineer by training, graduated from Northeastern University. And at this point, I have around 10 years of experience designing consumables and instrumentation for life science products, particularly with a microfluidics focus. So previously, before Parallel, I was at an organ-on-chip microfluidic company called Emulate. And then prior to that, I was at a mechanical engineering consulting firm called Fixed, where we worked on a number of different microfluidic technologies. And so who are we at Parallel? We are a rapid manufacturer of microfluidic devices. And our goal is really to help make the development process easier for people like yourselves so that you can focus on the science rather than having to worry about manufacturing of devices and some of the more general engineering problems that you face in microfluidic applications. So jumping into some of the basics of different manufacturing processes. So there are a number of different ways to form microfeatures into microfluidic devices. And in particular, on the prototyping side, there's a couple different categories. So on the subtractive side, you have laser machining, where you're using a laser to ablate material, usually from a rectangular piece of stock. Or micromilling, where you're using a CNC milling machine to cut channels into some sort of thermoplastic blank, typically. Probably the most common method that you all, I'm sure, have seen before is PDMS casting, where you're casting silicone onto some type of mold, whether that's a SU8 master or a machined mold or even a 3D printed mold. It's a very common technique at the prototype scale, especially in academic labs. And then finally, we have additive processes like 3D printing, where you're printing your device from scratch. And then on the production end of the spectrum, there's the whole world of glass, and you have etching processes there. You have hot embossing, but really probably the gold standard for microfluidic device production at the commercial level is micro injection molding. And the reason for that is that you can get really, really high volumes of products per year out of an injection molding process. The price per part comes down pretty low. And so when your design is locked and you're at full scale production, micro injection molding is a great way to form microfeatures into your devices. But the challenge with micro injection molding is that a mold cost can be anywhere from $50,000 plus, and lead times are usually measured in months. So 3 to 5 months maybe being the average. You might be able to expedite a little bit, but you all know that microfluidic design is iterative. And so if you're trying to jump straight into injection molding from the very beginning, it's super time consuming, super expensive, and can lead to some real problems there. So the natural thought is, okay, I'll use one of these prototype processes. But a major problem in microfluidics is that the prototyping techniques that I described are not necessarily representative of injection molding. So on the subtractive side, for instance, the design rules are very different than for an injection molding process. Or for PDMS, for example, the materials are so different that they're not a good representation of the high volume thermoplastic injection molding process. And when you eventually iterate through your design in PDMS and then try and make the switch to injection molding and to thermoplastic specifically, you can encounter all sorts of changes in the way your device performs, which leads to a variety of problems. And so that's our goal at Parallel, is to really try and fix this gap between prototyping and production. So we have our own proprietary technology here that we call transition molding. And what we can do is we can create representative prototypes 10 times faster and cheaper than injection molding, allowing you to iterate through the design process, but still retain the performance that you would see in an injection molded product. And so now we can jump into some of the fundamental challenges specifically in molding-based processes. So a lot of this will be specific to our process here at Parallel, but it's also transferable to injection molding. And just to step through, what does the molding process actually look like here? At its most basic, on the left, you see we have an illustration rather of an open mold. So we have some proud microfeatures on the surface. You will then close that mold and then fill it with thermoplastic resin. And then you need to somehow remove the device from the mold. So that's the ejection process or stripping process. And in molding-based processes, there are a couple really fundamental shared challenges, both in our process and in injection molding. And so one is that most molds are produced by CNC micromilling. That's not always true, but in a lot of instances, you're using a CNC machine to cut your master tool. Or even if you're not milling the tool directly, you will need to mill an EDM electrode for electrode discharge machining. So you're machining an inverse of the part that you actually want for the tool, and then sinking that into a piece of steel or aluminum and electronically machining the tool there. But both of those different methods require you to use these small rotary end mills to actually create your geometry. And there's a bit of a lower limit there. For us in-house, we typically run 100 microns as the smallest diameter end mill. So the picture that you see here, this is a comparison of a 1 millimeter diameter end mill and a 100 micron end mill. And you can see just how small that is, right? You can barely see the cutting tool at the end of the shaft on the right there. And typically the maximum aspect ratio that we can achieve with a milled solution is a 3:1 aspect ratio. And if you know that lower limit, that helps to inform a lot of the design guidelines that we'll talk about a little bit later on. And just one quick design tip before we move on is, in your parts, if you can design them such that the tooling generation process won't require these really, really tiny end mills, it can help to reduce cost and improve the overall accuracy of the part. Moving on here, another shared challenge in any type of molding process for thermoplastics is that plastics shrink as they cool. And so you'll inject your molten plastic into your mold, and then as the plastic cools back down below the glass transition temperature, it's going to shrink onto the mold and really grab on to any of those proud features that are there. And as it shrinks, the ejection can become difficult. And difficult ejection causes all sorts of problems, which we'll elaborate on in a little bit. But at its most basic, two questions that you can keep in mind while you're designing your parts are, can I cut the mold and can I eject the finished part? And if you're constantly thinking about these two questions while you're designing, it helps to make the development process easier and makes it so that you'll have a good idea of if you're set up for success when you go to actually produce your prototype parts. And these two questions will really inform the specific guidelines that we'll talk about as we move on here. So now jumping into guidelines, again, kind of specifically for our process here at Parallel, but a lot of these different rules are transferable to injection molding because it's a really similar set of design constraints. And before we get into the details, just to kind of set the stage here, for the purposes of this webinar, we'll talk about a pretty basic layout for a microfluidic device where we have a fluidic layer, which has all of your microfeatures and your channels. This is really like the heart of the microfluidic device. You have a cap on the bottom, which seals those features. And then on the top surface, one thing specifically we can do here at Parallel is we can add different components to achieve a few different objectives. So you see a threaded fitting here. These are compatible with like HPLC style connectors. So now that we know the basic setup for the microfluidic device, the first thing to touch on is capping. So the capping technique that we use here at Parallel is a thermal bonding technique. And so we're taking a thermoplastic sheet that's the same polymer as the base fluidic layer and thermally connecting it to the fluidic features. So we use heat and pressure to attach the two to each other. The standard thickness is 250 microns. And one rule to keep in mind as you're designing is best practice is definitely to keep a little bit of an offset between the extents of the cap and the edge of the device. So you can see it called out in the image on the right here. And the reason for that offset is that it helps to create a more robust joint between the edge of the cap and the body of the fluidic layer, and makes so that if you're handling the parts, there's no edges that can snag and potentially rip the cap off in handling or shipping or just in use in general. So definitely a best practice that we recommend on the capping side. And now looking at channel dimensions. So channels obviously are one of the most important things in microfluidics. And so the general guidelines here are that in height and width, 50 microns tends to be the smallest, like comfortable cross section that we can hit without a little bit of a further conversation. And then on the maximum side, width doesn't really matter. We can make them as wide as you want, but the height of the channels should be 70% of the thickness of the device or less. Anything above that, you start to run into some issues during the molding process. And as a general rule of thumb, that will be true in injection molding too. You want to avoid really thin sections in your parts. And so now 50 microns is the minimum, but I would say that if you can, a good nominal size to shoot for is between 100 and 200 microns, because it adds it helps to balance the size of the channels to general manufacturing tolerances. So we'll talk a little bit more specifically about tolerances later in the presentation here. But if you just assume, say you have a tolerance of plus or minus 20 microns, then if you have a 200 micron channel, that's only a 10% change in channel dimension due to tolerances. If you have a 50 micron channel with the same tolerances, obviously that's a much bigger swing. So if you can stay in that 100 to 200 micron range, that really tends to be a good go-to size if it's applicable for your particular project. Of course, there's plenty of applications that require smaller sizes than that or larger, but just a good kind of general rule of thumb to follow there. And smaller dimensions than 50 microns are also totally possible. It's just more of a case-by-case basis, and we'll need to review specifically to make sure that we can hit whatever dimensions you need there. But 50 microns is a good, safe, lower limit to choose. Now, related, jumping into the aspect ratio of a given channel. So again, we're looking at a section view through the device here of a channel. On the left, we have a low aspect ratio feature. On the right, we have a high aspect ratio feature. And so for uncapped devices, there's no minimum. They can be as wide as you want and as short as you want. And the maximum is 2 to 1. And that gets back to the fundamental challenges we talked about earlier of being able to fit your tools in there, and also making sure that you don't have these big vertical surfaces that are getting grabbed during ejection that can make things problematic. So 2 to 1 is a good upper limit to shoot for if you can. And then for capped devices, we do have a lower limit there of about 1 to 10. And the reason for that is since we are using a thermal capping process here, if you go much lower than 1 to 10, you can end up with bowing of the cap and deformation where it essentially like sinks into the channel and obstructs the channel partially. And we found that over a 1 to 10 aspect ratio, you start to run into those issues. There are a couple tricks to design around that if you need to. And we're happy to talk about those further for any specific application. But in general, if you can stay above 1 to 10, you'll be in much better shape. Low aspect ratio features tend to eject really well, but high aspect ratio features have an advantage in that if there is one, there tends to be much less deformation in the capping process. And then two, that any deformation that you do see will be a smaller percentage of the total height of the channel. So it can be a little bit more robust there. 1 to 1, typically a pretty good compromise if you don't have a particular need to go one way or another. Now, draft, again, this gets back to the fundamental ejection problem that we talked about earlier. Draft helps you eject in basically any situation and can be really useful. And so it's defined as the angle of taper from the pole direction of the mold. So looking at the section view here, our mold's going to open in the vertical direction. And by having those sloped surfaces, it just makes it so that shrink effect of the plastic doesn't cause the part to drag on the tool on the way out. And that helps to solve all sorts of problems and prevents things like drag marks or particulate from forming in the ejection process. With microfeatures, you can often get away with not having draft, but it's important that the feature heights are less than 200 microns for that to be the case. Anywhere you have features that are above 200 microns, we typically recommend a 2-degree draft overall, just to help in the ejection process. And one other quick design tip here is just that if you can keep a common draft angle on all of your surfaces, it really helps us to improve the overall accuracy of the part. We don't have to change tools as often, and it can help to reduce the overall part cost for an iteration of parts as well. And then corner radii. So, all of these guidelines tie back to those fundamental challenges. And so since 100 microns is the minimum diameter tool that we run, any external microfeature in your device is going to require a 50 micron or greater radius. So in the image on the left, we can see there we're pointing out where the radius should be in this design here. And then sharp internal microfeatures are internal rather than external, like you see in the left here, are possible, but not recommended. Again, during ejection, they can cause issues there. It can be hard to fill plastic into sharp corners too. So the best practice, if you can, is to have an image, or to have a channel rather, that's shaped more like the image on the right. A nice smooth channel that has some large radii on it allows us to use larger tools, and subsequently can lower the cost of producing the tooling for your parts and solve some of those problems that you could see in the situation where you have sharp corners. Onto vias. So vias are what we call through holes that connect the top surface of your device down to the microfeatures on the bottom. And one thing that's important to note is that here at Parallel, with our transition molding process, we are post-machining the vias. So we're using a CNC machine after the fact to either drill or mill the vias through your part. And since that's the case, it's really important to think about burrs in that process. Just the nature of machining plastics in general, you constantly need to be thinking about burrs and where are they going to end up and how do you prevent them. And so if we look at the common via design that we see here from a section view, so on the left, we have the design geometry that we want. And the way that we're going to form this is we're going to mold the channel. So that's this section here, and the mold is going to look something like you see in the middle, where the channel is going to extend a little bit into where the via would be here. We're going to mold that in place. You'll have to use your imagination a bit. The hole wouldn't normally be here in the molding process. And then over on the right is the post-machining step. So we're going to take a drill on the CNC machine. We're going to plunge down and then meet that microfeature at the bottom. And the most important thing here is that you can see the corner where the microfeature in the channel, in this case, meets the drill. That's a really high risk area for a burr because you have a tool that's exiting the plastic into open space there. And you'll often leave a little small vestige behind. And that's a particularly problematic area to have a burr because it's at the entrance to your channel, and it can snag particles, it can trap bubbles, there's all sorts of bad things that can happen there. So what we really recommend, if it works for your design, is a via design something like this, where if we look at a section view, you'll have the same straight section at the top of the device, but then it tapers down to a drafted section at the bottom. What this allows us to do is mold that drafted section into place from the beginning. And then when we go into the post-machining step, the drill, rather than meeting the channel, is going to meet that tapered, the tapered section that we've molded in place. And so now, if you do get a burr, the risk of that is, one, already greatly diminished, and two, it's going to happen up in the via where you have a larger diameter hole. And so if there is any kind of burr left behind there, it's much less likely to trap a bubble or to cause obstructions in your flow. And so that if you can work with this particular design, it really helps to make the products more robust for you. Moving on to posts. Posts are a really common thing that we see in a lot of different customer parts. So these will be proud features like you see in the section view here, inside of a larger microfeature. And again, thinking about that 100 micron lower limit for our tooling, the minimum diameter there we can do is 125 microns because we need a little clearance to actually get the tool in the first place. And then the distance between posts can be as low as 50 microns though. So it can be pretty close together there, and the same aspect ratio still applies. Now, on the other hand, wells are the inverse of posts here. So the two dimensions are flipped. So the distance between the posts is what's driven by that 100 micron tooling. And the diameter of the posts themselves can be pretty small, down to 50 microns or so, could even be smaller if you needed it to. But one thing to note with wells is that they're really grabby in that ejection process, and the plastic really likes to stick to them. And so the plastic really likes to stick to the tool in this case. And if you have a high density array of wells, which people often want to do, we really recommend draft there. So again, like 2 degrees, if you can fit it, is great and really helps to improve the ejection process. And specifically speaking about ejection here, so this is just a photo of a part that we produced in-house. You can see all of these little circles that are in the image here are ejector marks. So they're from the ejector pins that are in our process. And that is similar between what we do here at Parallel and what you would see if you went to injection mold these parts in the long run. So the thing to know there is that usually the manufacturer is the one that sets the ejector layout, but the important thing is to leave space so that we have a spot to put the different pins. Our standard sizes are 1.5 millimeters and 0.75 millimeters in diameter. And you can see in this particular part here, maybe the best example is we have a couple pins that are inside some higher density arrays, or not arrays, but rather sections of microfeatures here, which helps us to eject the part. So if you leave us a little space like we had in here, that allows us to place a pin and improve the ejection process. The standard tolerances in our transition molding technique are typically the greater of either plus or minus 20 microns or 10% of a feature dimension for microfeatures. So that's like all your channels, all your features when you're looking at them in cross section. And then on the more macro side, typical machining tolerances apply. So plus or minus 125 microns, plus or minus 5 thou, same thing. And that includes the outer dimensions of your device and any like via to via positions. So these are the starting point, but we can hold tolerances if you need to. It's more of a case-by-case basis. We just need to talk through a drawing with you, make sure that we have the spec really figured out before we would commit to doing anything that's tighter than that. But there are certainly options there. So that's it for the design guidelines. So just quickly, I'll chat through why you might use our service here at Parallel. And in short, it's because we're going to be 10 times faster and cheaper than micro injection molding to go through an iteration of a device. So you can expedite your parts to as little as 3-day turnaround. And we also can include what we call our embedded components in your device. And we have a couple of formats available that are pre-built, essentially like layout templates for your device that are compatible with some of our different accessories. So you can see here, like we have the microplate adapters stacked in the background, which match for this microscope slide format template that we offer. So just to expand on that a little bit more, components are available in either prototype quantities or high volume. In this photo, you see these are the same threaded flat bottom fittings that can connect to standard like IDEX, HPLC style adapters. We're welding those directly to the device, so we're not using adhesives or anything like that. And we also make the CAD available for the components, so you can just download them, add them to the assembly of your device before you upload, and then they'll be included right in the quote. And it helps to solve that challenge of creating the chip to world interface, which can be really problematic for a lot of folks trying to create their own devices, especially for the first time. And then the core formats. So these are 3 standard templates that we're offering. One is a microscope slide that you see here. There's also a double slide template, so just twice as wide as a normal slide. And then finally, a weld plate insert, which is the same, or rather it's compatible with our microplate adapters, and it has the same spacing as the internal area of a 96 well plate. So if you're trying to interface with existing lab instrumentation, it can make that whole process a lot easier. The core formats are all guaranteed to be compatible with our components. So like the fittings that I mentioned earlier and the accessories, so the plate adapters for now. And also with the core formats, you automatically get expedited from our standard, from 2-week lead time up to a 1-week lead time at no charge. So it helps you to really iterate through that process quickly without adding any extra cost there. And then finally, we have our web app. So instead of playing the game where you send an email off to somebody for quote, and then maybe you'll get a response back in a week or two, you just upload your design straight to our website. We'll give you design feedback right through the web portal. You can make changes to things like material or like what capping method you'd like to use, adjust quantities on the fly, and see all the pricing update in real time. Again, just to try and make that design process so much faster, because the week spent waiting for a quote is just as valuable as the week spent waiting for a part. So we're trying to make the whole process faster here. And yeah, I guess with that, I'd say if any of you have a design that you'd like to quote or you'd like feedback on, feel free to just upload it at parallelfluidics.com. And then after the webinar here, we'll make sure that we post the webinar and a version of these guidelines online. We're mid relaunch of our website right now, so probably later this week we'll have the new site up, and then you'll be able to see all these guidelines just directly through the website. So yeah, with that, thank you very much. Feel free to reach out to me directly by email if you have any questions or would like to talk about an application. And with that, I think we'll switch it over to Q&A.
Awesome. Thanks for a great presentation, Josh. I think we covered definitely a lot of information there. We certainly have a few questions here that we'll do our best to get through. So a reminder, if you do have questions, feel free to click the Q&A button in the bottom of your screen, and feel free to ask your question in there, and we'll try and get to as many as we can before we wrap things up. So first question that I have here, is it possible to alter surface chemistry of the plastics you make in your chips?
Yeah, so the surface chemistry, that's a good question. So right now we're not coating chips at all. However, one thing we can do is we can corona treat devices to at least temporarily make the surfaces more hydrophilic. So it wouldn't be the kind of thing where if you wanted to store parts on the shelf for 6 months, they wouldn't be hydrophilic after that anymore. But if you're going to use the parts in a couple days, they will definitely be more hydrophilic there. However, that is one thing that is on our product roadmap. I guess I didn't mention much about us as a company and our history, but we're a pretty young company here. So our capabilities are going to be constantly changing in the future, and adding particularly hydrophilic and hydrophobic coatings are certainly on the short list for us.
Awesome. A question with regards to the minimum channel width. You know, it's I just want a clarification on what the smallest end mill size that you guys have that are working with. Was it a 100 micron OD or something else?
Yeah, so there's a couple, I guess, aspects to that particular question. So 100 microns is the smallest OD end mill that we run. However, you need to keep in mind that we're machining the tooling that's used to create the part. So the OD of the end mill doesn't actually drive the size of the channels. We can make channels that are smaller than that 100 microns. 50 microns is typically the lower end of the spectrum before we need to have a more in-depth conversation about requirements. But I would say like 50 microns is a good lower limit for channel width and height.
Great. Can you can you ensure confidentiality as far as designs go, you know, with customers sending in CAD files and such?
Yeah, definitely. So I guess the thing to say just right off the bat is that we keep all of our customer information confidential. And the way that we do that now is we have a set of terms up on the website that explains exactly how the CAD is kept confidential. So the easiest thing is just if you go through the upload process, you'll be able to see those terms and read them and make sure that it works for you. But it should be as easy as just checking the box when you upload, and it ensures confidentiality throughout the process.
Great. Is there a preferred draft angle for better surface finish on machine parts or quickly made tools?
So that's a good question. Yes, we can get some essentially like tapered end mills, which make it so that we can clean up the walls of the surface in one pass. And so there are a couple different angles that we can get off of the shelf. I would say that, you know, a 2-degree taper is something that really helps on ejection, and we know we can get those off the shelf. And so if that's an option, yeah, I think 2 degrees is a great place to start.
Great. And then back onto the connectors, are you offering other connector types? And then for the ones that at least were shown there, what sort of size tubing are we looking at for those?
Yeah, so we do offer a couple different connector types. So we have the flat bottom threaded fittings. We also have lure fittings. And then the one that will be added shortly when we put the new version of the site up is like a gravity reservoir, or a reservoir that can be used with an external manifold. For the flat bottom fittings in particular, they're sized for a 1/16 inch tubing right now, which is pretty standard. You can actually use them with smaller sizes too, the 1/32 tube. But we designed them around the 1/16 inch tubing. We provide the female port, and then you will have to buy the male fitting from IDEX or Cole Parmer or one of the other suppliers for that sort of stuff. But it's all off the shelf.
Great. Is the capability today set up to do multiple fluidic layers in your devices?
So right now we are really mostly set up to do single layer devices. Again, multi-layer is on our short list up there with different coatings. In particular instances, we might be able to do a certain type of multi-layer design. So whoever asked that question, I'd be happy to chat offline and see if that would be a possibility.
Awesome. And then back onto the vias, a couple questions there. So see, what would be your best recommended angle for those vias?
For the vias, the recommended angle there, we're sort of flexible on. I would say, you know, like a 5-degree angle would be great, but and anything like above 2 degrees is probably good.
Awesome. And then as far, again, on the vias, you mentioned that they're post-machined. Can they be molded through the full thickness of the device? Maybe if the draft angle is a certain way, or the geometry is a certain way, or are they always machined?
Yeah, they're always going to be machined. The thing we could do is we could, I guess, mold more of the via. Like in my little sketch I had drawn out, the molded portion of the via probably only went maybe 20 or 30% of the way through the thickness of the device. We could probably go up to like that 70% upper limit there, and then have the machine joint be much higher, be away from the area where the channels actually are. So we can't go all the way through, but we can at least move the joint closer to the top surface if that would be helpful.
Great. And then as far as the fittings go, you say they're welded on. Is that ultrasonic welding? And then what, is there anything else that customers should be considering as far as the welding process?
Yeah, so the fittings are welded on in an ultrasonic format right now. I guess other things to consider there are that the nice thing about the welding is that there's no glue. The drawback of the welding is there can be a slight amount of particulate there. We've really tried to optimize that technique to reduce that particulate overall, and the joint is designed in a specific way to try and eliminate that. But there is always that small risk with the ultrasonic technique.
Great. And then I guess, further down the line, and maybe you don't want to commit to this quite today, but, looking at that 50 micron minimum feature size, what do you see the future? Do you see stuff getting down to, maybe 10 microns or something in that range?
Yeah, so I think one thing that would be, I think we're trying to define what the lowest range is right now that's useful for our customers. I would say that 10 microns is probably in the realm of possibility in the future. There's a couple different techniques we think we could incorporate into our process to go even smaller. But right now I would say 50 microns we set as a lower limit. But if you really needed to get down to 20 or 30, we might be able to do that for a specific application. I think 10 is probably out of the question as of right now. But a year from now, that might be a very different case.
Awesome. And then last one, just to wrap it up, can you talk through some of those other components that you offer and sort of what the uses are there?
Yeah, sure. So like I think I mentioned earlier that the other components we're offering right now are a lure fitting in addition to the flat bottom tubing fitting, and then the other main one is a just gravity like conical bottom reservoir. So it'd be pretty similar to what you see in a microplate, except attached to your device, and that could either be used for gravity driven flow or potentially to mate with an external pressure manifold. It'll have nice smooth corners on the top of it if you want to press it up against a seal. And so those are I guess like the minimum products that we have launched today. And that is one of the goals for us as a company, though, is to develop a real suite of products that our customers can use here. So it's a little bit early days on the component side, but things that are on the short list for sure for components are embedded valves, with either pneumatic or hydraulic control, and onboard pumps, integration of electronic sensors. We're really trying to solve some of those more engineering related tasks to allow our customers to stay focused on the science. So this might be a little bit of a wishy-washy answer since we don't have a lot of that stuff launched yet, but I would say in the next coming months, we'll release more of those components, and we're happy to keep people informed if they're interested.
And then just last follow up on that one, those components have to be used in parallel chips, or can be used, just with the components with other, maybe larger scale manufacturing?
Yeah, so they definitely could be transferable to large scale manufacturing. So we'll be producing them in high volume so we can supply them at high quantities if you make the jump to production, and they could be used with like a third-party CM contract manufacturer, for instance. It's not necessarily something that we need to do here at Parallel. We're not planning on selling like small quantities like retail right now, but if you do want to make the jump to full-scale production, we're happy to supply those high volumes.
Great. At that, I'll wrap it up for this webinar. Thanks everybody for joining us, and thanks Josh for the great presentation. A lot of good information, good questions. Within the next 24 hours or so, you should get another email from us, and that will have the recording of the webinar as well as a couple of extra links and things to follow up. And then, of course, feel free to reach out, hop on the website to learn more, or reach out directly to Josh, Josh at parallelfluidics.com. And we'll be more than happy to answer your questions. Thanks, everybody, and have a great day.
All right. Thank you all.